Professor George Yorgos Chrysanthou in today's colloquium. Yorgos is a professor at the University of Cyprus in the Computer Science Department, and he's also the research director of Science, one of the teaming projects in Cyprus. The focus of Science, of that research center, is interactive media, smart systems, emerging technologies. George is very well known in the area of computer graphics and many other things, robotics and so on. He has graduated a number of PhD students that are actually now forming a critical mass of researchers in Cyprus in the area of graphics and interactive media. A little bit of a personal story. As you may know, some of you, when I first came to Cyprus a year ago, I did a sabbatical, and the first half of the sabbatical was at Science, and Yorgos, he was the very first person I met in Cyprus. So when I think of research in Cyprus, my brain remembers Yorgos. So please welcome Yorgos Chrysanthou.
Okay, thank you, Sandino, and thanks for inviting me to give a talk at this great colloquium. It's my pleasure, my honor to be here. So I will, since I cannot walk up and down. So since I have you here, I will do a bit of advertising. So I will tell you a bit about our center, because I'm sure there's plenty of potential for collaboration. So the Science Center started us with funding from from the first teaming call, and it was called RISE at the beginning, Research Center on Interactive Media, Smart Systems, and Emerging Technologies. So it was set up in 2018. By a consortium of 5 academic institutions, UCL, Max Planck Institute in Saarbrücken, University of Cyprus, the Technological University, and the Open University of Cyprus, and it's coordinated by the municipality of Nicosia. Now, our area of interest, research area, is interactive media, and by that we mean kind of all technologies that involve interaction between user and the machine. And this is quite a broad spectrum with applications in almost any sector of industry and daily life. And of course, there you see the smart specialization of Cyprus, at least what we wrote in our proposal that we will work on. So one of the key points of our center is interdisciplinarity. You know, due to their nature, interactive media applications, they are very multifaceted. So in order to solve problems in a holistic way so that they have real-world applications and also always take the user into account, we had to bring together a multidisciplinary team from different backgrounds: computer science, psychology, design, multimedia, human factors, AI, and so on. So these are expertise that are kind of complementary, and together they have synergies that make our center, give it the strength that it has. And of course, this is something that you couldn't find in one specific department of our universities when we started. So over the last 5 years, we've been setting up the center. We have about 125 members of staff, plus some associated professors, 20 small research teams, a software development team, and a fairly strong innovation department. So this is our teams. I will not read this. I just say our research teams can be separated in 3 different research pillars. The first of them is the visual sciences, where we have teams that work on imaging 3D. We have a team on smart cameras, a team on 3D modeling and reconstruction, scene understanding. We have computer vision, graphics, animation, and we have a couple of teams working on virtual reality with applications in health and in different areas, and also in augmented reality, looking also at some of the other modalities like sound and tactile feedback, not only visual. Now, the other set of research teams is human factors and design. Here we have teams that look in specific, the cognitive and psychological aspect of the human factors for interactive media, but we also have more domain-specific teams. So educational technologies, museum technologies, art and technology. We have an occupational movement group that looks at disorders, and environmental informatics. And finally, we have a set of teams that are working in communications and AI. One team that looks at networks, 5G, 6G, smart networks, quality of service, and several teams that look at AI, both from the classical reasoning approach, also, but also machine learning, reinforcement learning, and also a couple of teams looking at fairness and transparency and ethics in AI, which is kind of getting quite important. So we set up our labs, motion capture, psychophysics, Internet of Things, virtual reality, robotics, all sorts of things. We have a nice machine learning server, which is hosted by the Cyprus Institute. Thank you very much for running all our because most of our teams work with machine learning. And recently, we set up a virtual production studio. We got one of the theaters of the municipality, the Theatropolis, and we set up a nice setting with a huge screen and motion capture and cameras and whatever. So we're ready both for research and for small productions if anyone is interested. In terms of funding, we've been doing well. We have tons of projects. I think we have about 45 funded projects running at the moment, both locally funded and European. You see some examples here. I will not go through them. I will just say that actually we've been doing really well. I'm proud about this. So if you look at the last 9 years, even though we're only 5 years running, we rank 4th in Cyprus in terms of funding. So, you know, considering that we only kind of sped up the last 2 years, I think we've done quite well. Okay, I will only mention one project and then I will finish and then I will go to the research part. So this is our flagship project, the Nicosia Digital Twin. So the idea here is that the municipality is laying currently the smart city infrastructure with cables, sensors, wireless, and so on. And actually, their terminal is in our building. We're not running it, but it's working closely with us. So we're building on top of that an application layer and a digital twin of the city, where by digital twin, we mean we scan the city. Actually, this is an old version. We have a lot of detail for the whole old city and quite a bit outside. And now we're in the process of connecting the 3D model with the sensor so that you have in real time a 3D representation of what's happening in the city, where you can run simulations like here at the bottom we see what if it rains, what if it snows, what happens to the streets, what happens to the lighting. You can run crowd simulation, you can run all sorts of different things. So this is one of the big projects we are running, and you know, if anyone is interested, we're very happy to collaborate and include more things. Okay, this is just a small section of the city that we used last year when at the Cyprus Forum, just to show the area that the Cyprus Forum was interested. Okay, so that was for the center. Now I will talk a little bit, now I will go to virtual characters. Now, someone might say, okay, why do we care? You know, we're engineers or physicists, you know, who cares about this 3D? But actually there's many, many applications that are using virtual characters, and these are increasing more and more. Of course, the most obvious one is computer games. We see it down there, Uncharted 4. This is quite an old game. Nowadays, the virtual characters look amazing in computer games. It could be the movies. Up there, we see a reel from Golem, where actually it's an example where almost wherever you see a lot of people in movies, they're not real. They're computer generated. You might have simulation, training. Here is a scene from a VR application on treatment of phobias, and so on. So there's many, many applications one can think where you need to use virtual humans. And actually, creating the virtual humans is quite a hard task. Maybe someone can say it's maybe one of the few remaining unsolved problems in computer graphics. And why is that? Because, first of all, our matter subject is difficult, it's deformable, it has a lot of detail, but also, and it's not a geometric, well-defined. But also, as humans, we are used to looking at the other people in the face for the detail, for the small movement, the small expression in the movement, in their motion, in the face, and so on. Because from that, we gain information about the other person. So whenever you do the smallest mistake, it's clear and it looks kind of scary. So what do you need to have virtual humans? First of all, you need to model them. Of course, the modeling, you need to model the surface. You don't care about the inside unless you're doing, I don't know, medical applications. And the surface is usually polygonal or triangular. And then you need to add the texture and the reflectance properties. This can be done either with scanning or with photogrammetry, or maybe you can download one of the ready software that has ready models, and then they use AI to customize it to your face if you want. Then you need the rendering. Yeah, you have the model. There we have our cow. You define the lights, you define the camera parameters, and then you take it through this pipeline where it does a lot of projections and physics and computer elimination, and it gives you the final rendered image. And then once you have the two components, then you come to the behavior and animation. So this also has a lot of layers. At the highest level is the decision making. What do I want my avatar to do? Maybe I want my avatar to go shopping. I want them to go to the other building to follow a talk or whatever. So that's the decision making. Then you have the path planning. Path planning is what's the most efficient or effective way to get there. And then you have steering, which is on your way, how you interact with the objects and the other characters, and finally the animation of the body. So I will talk a little bit about the steering and the animation, which of course, as I mentioned before, it's not easy to do it with a procedural method because it's not necessarily governed by physics and mechanics. Of course, physics plays a role, yeah? I mean, if I fall, I'm going to follow Newton's law. It's not, but it's not a mechanic thing. If I see a person, even from behind, I might know who it is from the way he or she walks. You know, if I see the gesture someone does, so the movement conveys character, conveys personality, mood, intention, and so on. So you cannot really so easily do procedural methods like you do in many other areas of graphics and science in general. So that's where we use a lot of data-driven approaches. So I will talk about two things briefly about steering. When you have a lot of people, how they interact and how they move in space, and animation, how you model the body, the movement of a body of a character. So let's look at the first one. Say you have a lot of people, a virtual crowd. Here on the left, we see an example of a procedural solution. You can see it's quite old. I mean, you have better solutions now, but it doesn't change. What we see here on the left is a method that is very efficient, scalable, robust, whatever, it works. But if we look in real life, we will see that's a huge difference. In real life, people stand together, they aggregate, they walk in pairs, they walk in, I don't know, they might change their idea on the way and do unpredictable things. They walk across the flow of the crowd. They do all sorts of different behaviors that you don't see in the procedural model. And in order to include all these behaviors, you need to have a lot of complicated rules, and you're not sure it's going to really work. So about maybe 15 years ago, we started working on this issue, and we thought, okay, the best solution is maybe use data-driven approach. So the method is simple. Say you have a virtual character, you want to know how he will behave. So you look at the real world, you find a similar situation, and you copy the movement. Yeah? So as a simple So in order to do that, you need to first define what does it mean a similar situation. So we define the state. So for every character individually, we place the character here at the beginning of at the origin, facing north, and we look at the people and the objects around this subject, and also the target, the intended goal. So this is the state, and then we have the action, which is the trajectory for a few seconds. Oops, wrong one. So I will not bother you with the old techniques, just to say that this resulted in a simple method where it's 2 steps. First, you start with real-world data, you track them, you create a database of examples, and then at runtime, whenever you have a character you want to know how he will behave, you look into the database, you find a similar situation, you copy a bit of the trajectory, and you continue. Fairly simple. But the result was quite impressive at the time, because you can see situations like real world, there is no collision, you have people walking in pairs, you have people standing at the shop window, you have people maybe waiting to cross other people and so on. These are behaviors that we didn't script at all. We just say, do what the real people do. And it worked really well. And we followed up with several works using action graphs, better states, secondary behaviors. This was quite successful. We had over 100,000 citations, and we were happy with it. But then machine learning came. It's been there for a while, yeah? But lately there's been a lot of development. So we thought, okay, our results were good, but maybe we can do better. So we looked at our previous work, and we said, okay, it works, but you can only simulate situations that are found in the original data. If you have situations that you haven't seen, then it breaks down. And you need quite a bit of training for that. And also, because you only take a few steps into account, it has no notion of history. So at some point, as soon as your simulation goes off the original data, then it starts breaking up. So we thought, okay, maybe we can use reinforcement learning. Yeah, reinforcement learning, although it's been there for a while, only the last few years it started being more, to us at least, because we tried it before and it didn't work, but lately it improved a lot. So in reinforcement learning, you try to teach your agent to find the optimal policy through a trial and error simulation, and there you define the tasks through a reward function. So, which is the tricky part actually in reinforcement learning. So we thought, okay, let's use it for our crowd simulation. So we have a reinforcement learning for crowds. So here is the loop. We have our agent that learns, and it looks at the environment with the state similar to what we had before. And here we're using deep reinforcement learning because we have a double deep Q-learning network that is our policy. This is our policy that we want to train. Okay, there's not that much, too much novelty there. What was our main contribution was that actually we went to inverse reinforcement learning. And the idea here is that the hard part, as I said, is to define the reward function. Because in order to define the reward function is equivalent to defining the rules by which your character needs to move. So in order to avoid this problem, which is actually not so easy to solve, we're using data. So the idea here is that we say, okay, take the reference data, track the trajectories, find the states, the actions, whatever. But whenever you want to calculate the reward, every time the agent takes a step and you want to see how good it is, then we use novelty detection to characterize this new move, how good it is in terms how much of an inlier is, meaning how close to real-world data it takes you. Yeah, so we're using K nearest neighbor, so we looked at the distance to the furthest nearest neighbor to give us a measure of how close you are to the real data. And of course, this, because it's probabilistic, it doesn't preclude doing behaviors that you see rarely It's just that you see them less often. And actually, this worked very well. It works very well. Here you see some of the training data. If we look on the left, this is a flocking, what we call is people walking together. This is people standing to chat, and this is people walking in front of a shop. And if we look at the training, we can see that actually, okay, at the beginning it takes a while. We can see that they lose the target, they don't know where they're going, but gradually after a number of iterations, our policy is learned and people move to their desired destination quite well. And
But still, the thing is that the agent tries to copy. The agent tries to copy.
no. The agent, sorry, let me stop it. No, the agent doesn't try to copy. The agent is using the data as the reward function. So the agent learns a policy, a deep a neural network. So it's using the neural network to generate novel movements. It's just that that neural network is trained using the data.
Not the motion.
Yeah.
Oh, okay.
So it's not copying, no. Yeah. Okay, so here we see that it does quite a few, you know, they walk in pairs, they go to their destination, they do all sorts of behaviors that we expect them to do. But more importantly is, if we look at the comparisons, the top is the original method, and here we see if we add a little bit more people, then they come into situations that they haven't seen before, and suddenly we get this mess. So once we get a little bit out at the exact thing that we saw, it gets messy. While at the bottom we see that even if we increase the density, which is something we haven't seen, so we haven't trained for it, there are cases where you get a little bit of disturbance, but our agent still knows their target, where it's going, so it's much more stable and it works much better. Okay. Now, this was one of the solutions. Now, we come to another problem. In this method, although we have a lot of different behaviors, all our agents are using the same policy. So essentially, it's a homogeneous population. It's just that they have a little bit of variety. Now, what if we wanted to have different types, different personalities? So here, we're looking at the method where we have people with different profiles, and we mix behaviors such as collision avoidance, goal-seeking, grouping, and interactions with objects of interest. So the idea here is to train, again, one policy, but allow us to change the profile of the agent depending on how the user wants each agent to be, and still be able to use the same policy without having to retrain. And the way we did it, sorry, I'm pressing the wrong button. This was a paper presented at SIGGRAPH last year. The way we did it is that we have the reward function. This time the reward function is manually defined, which has several rewards. For example, it has sparse rewards when you reach a goal, when you have a collision with objects or with other agents. It has dense rewards when every frame you look if you're going towards your goal, if you're going away, or if you're in groups, or if you're interacting with an object. These are static values, the rewards. But then we have these weights. These weights, the first weight it controls these rewards which are for goal seeking, then you have these for collision avoidance, for grouping, and for interaction with objects. And these weights are the profile of our agent. And then we enter that into our system along with the observations, and we train the network to do movements front, back, left, right. So again, we train our policy. And this time, once we did it, I mean, we train it. Here is just a quick thing on how we train it. We have the blue things are the obstacles, the red things are points of interest where people might want to start and look at. And we train lots of people together. But the important thing is that we train them gradually using a curriculum-based approach where we start first with only one weight. and we use only one weight to train them a little bit. Then we use more weights, but at the maximum value. We train them more, and then we keep on training them up to a point where we can use all the weights for the whole spectrum. So in the end, we train them with all the weights, and then we have this result. We have these buttons here. Here we say we want maximum interaction, so they go and stand next to the objects that they should interact. Then we say grouping. Without changing anything, they change their profile, they change their behavior. Or we say, let them move quickly to their goal, and we can see that they disperse, and so on. So in this way, we can manage to have one policy with lots of different characters, and you can see in here in a more complex environment, although the graphics is not very impressive, but it shows the result. Okay. So this is kind of just a short glimpse of what we do in terms of the crowd simulation. Of course, there's lots of things we can do more. We can add more behaviors. We can add, define a reward based on real-world data, like we did in the previous method, or even define our profiles using the real-world data. But there's plenty, and actually one of my PhD students is working on how you can define it using text-based solutions. So you can define your crowd using, yeah. Okay, so this was the first part, when you have many people interacting, but it's also, data-driven methods are also needed for the body. Yeah, because as we said, the way people move, it cannot easily be reconstructed using procedural methods. So here we used a lot of techniques that using dancing data, and the reason we chose the dancing data is because it's quite challenging. Think, for example, of modern dance. You know, it's unstructured, they can take any movement, any form. So if you can give a solution that can deal with that kind of data, then you can apply it to walking, to boxing, to kicking, to playing football, whatever. So we use the dancing as a hard example where we can solve our problems. So just to give you an idea of how the data is captured, here we see our dancer. He's wearing a motion capture suit. These sensors here with the lights, they're captured by the cameras. So every 3 sensors then define a bone. So then you define the skeleton. This is the skeleton. Actually, usually we render it with thinner lines. And then we can dress it and render it in a realistic environment so that you can get the full view. But the important thing is to have the data. So over the years, we've worked with, at the University of Cyprus and at Science, we've been capturing lots of dance data. We created the Dance DB library, which is actually the biggest library in the world with motion capture dance data. It's being used by scientists and artists around the world. And we have lots of different formats, if anyone wants to use it, from video to raw mockup to FBX, which is a skeleton. We even have the SMPL, the Max Planck format, which gives you also the skin surface once you add the skeleton. Okay, so we used we developed lots of algorithms over the year. For example, here we can see query by example. You give a sample and you say, find me in all my database what dance has this kind of movement. So here you can see how close the movement was. When it moves a little bit further, you're going to see it finds even closer movement. We did some techniques on emotion recognition. Some of our dances carry emotion. Some are faster, slower, sad, whatever. We developed algorithms for editing of style and emotion. Here our input is the middle one. We have the character who is moving normally, and then we say, we allow the user to move freely within the space of emotions in a continuous way. And they might say, I want it more angry, so suddenly the movement becomes more angry, or I want to be more bored, and you can see that it goes like this. So, and these are not predefined emotions. We have the full space of emotions, and the user can move. So we can edit the movement without changing the context. We just change the style. Yeah, and anyway, let's say,
In
okay.
this work,
So
we
let
present a
me
music-driven motion synthesis framework that enables
do the
synthesis.
sound a bit louder, because I think here, I'll show you 1 minute video, it says it better than me. So in our latest work, which is the last thing I'm going to show you, is we decided, okay, now we have modern machine learning techniques. Let's go a step further. Let's let our characters, allow them, train them to learn how to dance based on the music, creating novel movements, novel sequences, but of course within a specific genre of
In this work, we present a music-driven motion synthesis framework that enables synthesizing high-quality motions that are synchronized with the beat of a music signal. In addition, our framework provides control over the generated choreography, ensuring that the global content of the synthesized motion represents the culture of a specific dance genre. The main premise of this work is that motion sequences can be divided into small motion words based on the beat, which can be clustered into groups of motion motifs. The distribution of these motifs, which is represented as motion signatures, defines the global content of the dance. Such a representation can be used to distinguish between different dance genres and even between different roles within the same genre, such as leader and follower in salsa. Using signatures and motion words allows us to control the global content of the generated motions. In this work,
Okay, so if you manage to follow, the idea is that you have the beat, and we split the sequence into small sections within 1 beat each section, and that we call it a motion word. And we try to find similar ones, we cluster them, so we have a small set of motion words for each dance, and giving it the distribution of these motion words, each dance has a different signature. So the idea is that maybe the choreographer will come and say, I want my character to dance using this signature, using this music, for this amount of time. And the choreographer can change the signature as well. It will change the type of dance. And we built this architecture we see here, which is it has 3 components. 1 component to generate poses, 1 component to generate motifs, and 1 overall the choreography mixer that controls the whole situation. So the idea is, if we look at it, the first component, the pose component, takes the rhythmic features of the music as well as a desired motif that comes from the top layer. And then it generates 1 frame, 1 pose of animation. Yeah? But because it uses this LSTM network, it uses the history of the previous movement, so it creates a temporally coherent motions. Then if we go to the second step, the motif component, here first we collect the poses that come from the motion, from the first component, until we complete 1 beat. Once we complete 1 beat, then we take it through this add-in network that changes it, it modifies it based on the spectral features of the music. So it might make it more exaggerated, if it's faster, if it's harder, if it's whatever. So it changes so the output you get is not necessarily the one you originally had. And then finally, you have this motion perceptual loss that actually ensures that the motif you created is still a valid one and is not completely off. So it looks at your previous data. And then finally, you have the choreography mixer, which this one, it has the signature of that the user gave. So it's sending the desired motifs to generate the motions, to modify them, and it makes sure that in the long term, you stick to the signature that the user wanted.
Our network can generate high-quality dance animations that maintain the global content of the original choreography. Here, we can see that over time, the motion signature of the synthesized motion converges to the target motion signature. In this example, we generate two motion sequences using the same target motifs, but music with different beats per minute.
Essentially what we want to show here is that if you look at this character and this character, although they're dancing based on the same motif, one is more exaggerated, is doing different moves, and so on. So just to show that it's not just copying, it adapts it to what you do.
Here are more results from different dance genres. Here are more results from different dance genres.
This is not exactly the right dress, I know.
Our method is
But
capable
we
of
can do
recreating an
all sorts
existing
of,
dance
any
performed by
kind
a
of
professional dancer. We extract the sequence of motifs.
So this is, it's expensive to model clothes. So to conclude, we've seen a couple of examples of our work, one from crowd simulation, one from motion capture animation. Okay, compared to our previous traditional techniques, we have faster solutions, not faster in terms of training, but faster in terms of real-time runtime. Smoother animations, we can go a little bit outside the data, especially with reinforcement learning. And with reinforcement learning, you don't need that much data, actually. But of course, there's a lot of work that can be done. For example, what happens when you have someone wearing really heavy clothes? Because if you saw in our data, in our capture, they were wearing a skin-tight suit, yeah? But actually, this is the final result, and these are the different steps we took. Here is an example of an African dance. This lady, Temi, came from Holland, I think she's from Nigeria. And here, the difficulty is that when they dance in Nigeria, they wear these heavy clothes. So we did, you can see here, we captured both with the clothes and without the clothes. And the dancer, if you capture the dancer without the clothes, the performance is different than when he or she is wearing the clothes. So you cannot claim, yeah, I captured it and then I add the clothes using physics. It doesn't work. So we are looking on how we can capture people directly with the clothes and yeah, do the runner simulation. This project here from Christos Ioannou, this is actually quite interesting because here we start, I mean, Christos is a neuroscientist. What he cares about is to help people with musculoskeletal problems, to improve their posture, to improve their movement, because, and looking especially for athletes and musicians that have repetitive injuries, you know, from the movements they do. So we developed, or his team developed, this software that tracks the motion in every single muscle in the body, or the main muscles in the body, and it gives you information about the balance, the strength, the intensity, and so on. Okay, so you might say this is not very relevant, but actually it is, because our next project is to take the muscle information combined with the movement information and see if we can go from purely data driven solutions to physically based solutions, where we can activate the muscles and run the simulation. And this is an example of facial capture. This is Panayiotis, this is one of our team leaders.
Hi.
You can,
I can talk, I can smile, I can blink.
This was done, the motion capture was developed by us. We printed it in the makerspace downstairs in our building, and we did the whole process. So this is something we want to combine. The other thing is that I talked before about our flagship project, Digital Twin. We want to add crowds, yeah, but here we want it to be close to reality. So there are some cameras, some sensors in the city which we can use, but here we don't have enough data. So we want to be able to recreate the city as it is using sparse data. So we want to develop more robust algorithms for using less data. And this is some work we did recently. It's going to be presented in IEEE VR next month, where, again, using the digital twin, you have someone with a VR helmet in the lab and is working together in the real world with someone who's wearing an augmented reality helmet, and they're interacting together with the environment. This is just some examples of work that we're doing already, and it's all related to that. Okay, we have a project on performing arts using virtual reality. This is quite interesting. We're not just capturing, I'm finishing in 2 minutes, we're not just capturing full body motions for dancing. Here is a company that came out of our center. It's called Smart Cyclo, and they developed this technology along with us, where with 3 sensors you can capture the posture and help the cyclist be more efficient and less tired on the bicycle. So we're also doing work on sports, and finally we're not just capturing humans. Here is work of Andreas Aristidou. We helped Terra Cypria to capture lots of reptiles in Cyprus, and for a while we had snakes and lizards in our lab trying to recreate the movement. I mean, the guy had to go and encourage because the snake was a bit lazy, so we had to get it to move. So that's it. Of course, this is mostly not my work. And I want to, a big list of people who worked on this, but especially I want to mention Andreas Aristidou, who did most of the work on the motion capture, and Panagiotis Haralambous, who did most of the work on the crowds. Thank you. Thank you.
So we have time for many questions.
Thank you for the amazing presentation. So the first question I have is, have you used crowds? I mean, I would name it simulations. I don't know whether it's the right word to use. Regarding the propagation of viruses, for instance, related to, COVID, for instance?
Okay, one of our close collaborators in Spain, actually, I just came this morning from there, has done that. Okay. We haven't done it. We did some work on propagation of fear. So where that was before COVID, where you're in a situation and something happens, some people panic, and then other people see the panic, and then it propagates. But no, actually, we haven't tried the COVID. We didn't try.
Well, actually, the second question was related to what would happen in case of crisis. I mean, related to fear, and whether this could be used to build like buildings in a more efficient way.
Okay, and here I should give a disclaimer. We are graphics people, we're not engineers. We like to have things that look nice, realistic, whatever, but we don't have any ISO certification. We cannot tell you this is going to happen in a building. No. Okay. Although I believe our methods are quite realistic, and with the right tuning, they can do it. But it hasn't really been tested with emergency situation. And I mean, if you look at all this engineering work, they use dots and they do whatever, and they have methods that are not very realistic in what they look, but they correspond to real data. We haven't tested it against emergency data to be able to tune it to that level. We focused more on making it look realistic and behave realistic in a different way.
And finally, do you know if this kind of CAD simulations can also be used at different levels of magnitude, like molecular level or?
Yeah, I mean, okay. Here I have to say that this is one of the many things we do. Yeah. So many of these techniques can be applied elsewhere. You wouldn't maybe necessarily use the same data or the same, but the techniques can be applied, and the techniques can be applied also in emergency situations. We haven't tried it with that data, so to tune it enough. Yeah, but also in other situations. I mean, these are quite general techniques that can be used, so if anyone wants to try something, we'll be happy to try. I'm sure it can be applied.
Yorgo, thanks for the inspiring talk. You mentioned about the iNicosia project and the digital twin, and the fact that you have sensors in the city. Could you explain a bit on what kind of sensors?
Okay.
I mean, what are you sensing? What are you looking for?
That's a very good question. Right. That's a very good question. But actually, none of the sensors are ours. The sensors belong to the municipality of Nicosia. So the municipality, whenever they refurbish a street, and they've done quite a few in the city, and also Kallipoleos and Kyriakoumatsi and the Emporiko Trigono. So actually now, from this morning, we are scanning in high detail Makariou, and we want the next level is to involve the shop owners so that they can use the model for advertising or maybe showing even the insides of their buildings and so on. So we want to take it to the next level. But in terms of the sensors, it's whatever the municipality has installed. And from what I remember, I mean, they gave us a list of like 20 sensors. They have, of course, temperature, pollution, noise, but they also have parking sensors. They have cameras that track cars and pedestrians in many different places. They have, for the garbage sensors, they have for the light sensors. I cannot remember what else, but whatever sensor we would like to have, we can add it to their system. And actually, one of the things we discussed is maybe we can add a few more people sensors, that not necessarily cameras, but they can sense when people pass, so that we get more information about the movement in the city, so that we can do our simulation.
You mentioned pollution sensors.
Yeah.
Air quality.
Yeah, I mean, I don't know how good they are, don't ask me, but yeah, that's what in the list they gave us, yeah, it's, yes, they have a couple.
Okay. It's a follow-up of our discussion, what we were discussing before the talk. How are you interacting with the creative industries? I mean, you are generating methods, you are generating tools. Are you moving in that direction?
Yeah, absolutely.
Delivering them to the...
Absolutely. Actually, we have quite a few collaborations. I mean, one that I didn't mention, we have a collaboration with Sony Animation, where we help them to make the creation of the storyboards faster, using machine learning techniques that we've been using. We have a collaboration with the Cypriot Animation Association. We had, in November, they had a seminar on motion capture in our lab, and it was quite successful. It was full of people. And we now begin collaboration with all the small filming companies, or because they all want to use or try the new virtual production techniques. But beyond that, I mean, apart from our graphics team, there's a lot of collaboration with the makerspace. For the festival, for printing, for making things. Actually, we have a huge membership of artists in the makerspace that follow the center as a whole.
Are you spin-offing these methods? I mean, is something that you are trying to
Okay,
develop?
one thing that I didn't mention is that we created our own, apart from the cycling app, we created our own motion capture system. So it's sensors you put on yourself. It doesn't need cameras. It's using ultra-low band Wi-Fi. And we got funded by Cyprus and for the second round now. And we are looking into spinning it off into a company, yeah. Yeah, so, and also the one with the cycling, it's kind of a spin-off. It's two people that were working in the center in collaboration with us.
Thank you, Yorgos, for the really nice presentation. Even as a non-specialist, I think I learned quite a lot. Among other things, that you need to train your systems on real people, real movements, and then the system can do what it wants. And I understand you can use it for crowd control to test what happens if you do this and that, and then you can teach the real crowd how to behave in an emergency and things like that. What I was wondering is, to which extent can you push it to the level that the system, the model, trains an individual person, for instance, with their dancing?
Okay.
Can you use
Yeah.
your model to teach people how to dance a certain dance?
Yeah. We had a project that finished a few months ago with France and UK, where we were doing just that. So there's two ways we thought of doing it. One is through a virtual mirror, or the other one is with augmented reality, where you see yourself, but you have like a Kinect that scans your movement, and then it compares your movement with what you're supposed to do, and it gives you specific information on what you've done wrong. So when you look at yourself, you can see that you should have moved your hand, or you should have done it differently. Yeah, we tried that. I cannot say it worked particularly well. It's difficult. But we also developed a game where it's more natural to see. So you have a TV, it's like Let's Dance, but actually Let's Dance just tracks your hands, nothing more. While here we track the whole body, and then we give information. But actually there's a lot of work I didn't mention, that on dancing we don't just compare movements by looking at distances. In some other work that we've done, we compare movements using Laban notation. I don't know if anyone has done dance. It's the standard that the dancers are using, where it can tell you not that you haven't moved it high enough, that you're not going fast enough with enough effort, with enough whatever. So it gives you information that is more relevant to a dancer, because you might not have moved it high enough because you know, the scale of your skeleton is not the same, or whatever. So yeah. So we've done several different attempts to train people. We don't have a system that works very well, but
You're working on it.
we have a decent results.
Thank you for your talk. I have a question. Since you also have an ethics department, what are your efforts to making your simulations and your machine learning as equal and diverse as you can, and your graphics? Because, for example, the dancers you showed, especially for me, it was very telling. The female salsa dancer was basically as female as you can make a graphic of a woman, except for making maybe like a Barbie from the body type and from the body features.
It's a how do you call it?
I'm wondering.
Yeah.
Are you taking any efforts to try to make your machine learning and the results you have as diverse and equal as you can? Because as we all know, AI tends to become rather racist if it's data-driven, for example.
Yeah. It's true that we have two teams working on ethics and AI. In this specific one, We didn't, no. In this specific line of work, we didn't do anything. I have to admit. In other, because also it's kind of difficult because we track real people and we want to show, so if our dancers dance in a female way, that's how they dance. Yeah, so maybe we could do something, I don't know, maybe. But we've done a lot of work on that when it comes to asking queries on the internet and finding a more objective and transparent and more ethically correct solution. We've done a lot of work on that. But on the dancing, no, unfortunately, we just stuck to whatever the data gave us.
So I think this is not working. In any case, Yorgos, okay. So thank you very much, Yorgos. This was very interesting. I'm just wondering more from the modeling point of view, as a follow-up also of previous questions. How do the characters behave under conditions that are not in the training data set? Features, for example, rhythms in this example that you just saw now.
Yeah.
Do you get a specific pattern, or it's more like...
Okay. I mean, with the reinforcement learning, you can push it a bit because it still retains the target and the goal, and it has a policy, so it's more robust. With machine learning, if you go entirely out, we haven't tried. I mean, okay, then it starts to break down. So there is difference between the neural network, pure neural network solution and the reinforcement learning solution. Yeah, I don't know. Maybe an expert on AI could help us more on that. Yeah, yeah.
Thank you very much, Yorgo, for the great talk. I mean, I just had a general question, basically. Because, you know, I think that VR has a sort of, let's say, parallel evolution to AI in the sense that it's trying to make a breakthrough, something happens, people are disappointed, and they stop working on it, and they come back, la, 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 la. And now it seems that third time's the charm, this time with AI, right? So my question is, because we've been hearing the same thing with VR, let's say, since the 90s, right? Everyone is trying to become overwhelmed with VR, everyone is preparing, and, you know, nothing happens. But now we see also these great applications that you have shown with augmented reality, so you can walk with someone, and we see one of the big three companies, let's say, pushing very hard on that against the will of most of the employees. So basically my question is, you know, based on your long experience working on this, do you see something different this time? Maybe with AI or maybe with, no, I don't know, because I think one of the factors is that it's very cumbersome.
Okay,
right?
I think you're absolutely right. And I think indeed you see this super excitement and this disappointment and flat for a while and going up again. And you see it in both. Of course, both techniques are old. I mean, the first VR headset was in the 60s. It's not new. I think AI is more likely to stay for good than VR. I mean, VR will also, I mean, you know better for AI, but to me, it seems that VR, the AI is beginning to give some good results with lots of applications. It might not solve all the problems, but it has so good applications. With VR, there was a lot of hype, and indeed, Meta went crazy, but actually now they're closing down several of the research centers in the area. VR is difficult to find the niche. I mean, okay, gamers like to play. After a while, they get dizzy. You get a headache. You get and you cannot really move if you don't see where you're going. You cannot. So it's. I'm not sure it's gonna do a big difference. VR, AR, on the other hand, has a lot more applications because you can see the real world and you can interact and you can add information and you can add whatever. But I believe it's not there yet. VR is there. VR, you have good headsets, you can do good graphics, With AR, you still don't have good headsets. So, yes, I believe in the long term, AR will win and will stay, but not yet.
Is there any other question? I always like to ask the last question. And these days, of course, it's impossible to not ask a question related to ChatGPT and all of the generative models that everybody's talking about. So what is your perspective? How do you think this generative, especially the multimodal models, how will they change what you do?
Okay, I mean, for us, there's already a huge craze to use all these techniques. Actually, 2 of my PhD students are working on going from text to crowds, text to animation. It's not so easy. It's not so easy. I think if you look what ChatGPT is doing, it's great. It's amazing. I mean, I couldn't believe it when I saw it. But it's been trained on, I don't know how many millions and billions of different text. But when it comes to 3D animation, the data is not that much. I mean, we believe we have a big database. We have 400 dances, but it's not the same scale. So it's really, I mean, for us in general, I think it will change things. In other fields. In our field, it's going to take a while.
Thank you very much.
Yeah. Thank you. Thanks for your patience.